Module 2, Lecture B, Advanced Indexing. By the end of this lecture, you will be able to apply integer array indexing to select arbitrary rows, columns, and elements from ndarrays. Construct boolean masks to filter arrays based on element-wise conditions, and combine conditions with logical operators. And use advanced indexing patterns to modify subsets of arrays in place for data cleaning and transformation tasks. Integer array indexing. Row index arrays. Row index arrays let you select specific rows from a dataset by listing their exact positions instead of using a continuous range. This allows you to choose rows in any order, and even repeat rows when needed. You simply provide a separate array of row numbers, and the dataset returns only those rows. This approach is useful for irregular selections driven by external logic, such as particular customer records or experiment runs, and it lets you work flexibly with complex data without changing its original structure. Row index arrays let you pull out specific rows from a large dataset based on their positions. For example, in a clinical study, you can use them to directly retrieve the records of patients who completed all follow-up visits in exactly the order you want. The same idea applies to many fields, such as selecting certain days from stock prices, particular sensors from environmental data, or specific students from a class list. The key point is that row index arrays act as precise retrieval tools, allowing you to select non-adjacent rows without requiring any simple pattern in their positions. Row index arrays can do more than filter data. They can also reorder and duplicate rows based on how you set up the indices. By arranging indices in a new sequence, you can change the order of the data to help with sorting or grouping. Repeating indices will duplicate rows, which can be useful for aligning data from different sources. However, changes made through this new indexed array may not affect the original data, depending on the library. Understanding these behaviors helps you subset, reorder, and prepare data effectively for analysis. Python code. Row index arrays. This section shows how to use integer index arrays in NumPy to select specific rows from an array. By providing a custom list of row positions, you can pick out only the rows you want, change their order, or even repeat the same row multiple times. The goal is to help beginners see how changing the row index array directly changes the structure and arrangement of the resulting array. In this script, we use the NumPy library, which is a key tool in Python for fast numerical computations. NumPy is especially useful for working with arrays and performing mathematical operations efficiently. Here, it allows us to manage and manipulate arrays so we can select and reorder data based on specific indices. This makes handling structured numerical data both easier and more efficient. We create a small dataset using a numerical array to store the heights of 5 individuals. Each entry in the array contains 2 pieces of information: a unique identifier for the person and their height in inches. Organizing the data this way makes it easy to manage, access, and manipulate the height information for each individual. We begin by printing a short message to explain that we are about to display the original dataset, which contains person identifiers and their heights measured in inches. Then we output the array that stores this information for 5 individuals. Seeing this array lets us understand the initial structure and values of the data before we make any changes or perform further analysis. We can use a NumPy array of row indices to control which rows we select from another array and in what order. For example, choosing indices 3, 0, and 3 means we take the fourth row, then the first row, and then the fourth row again. This lets us both reorder rows and duplicate specific rows from the original dataset as needed. We use a row index array to directly control which rows we take from the original dataset. By applying this index array to the heights data, we can select specific rows in any order we want. This lets us reorder the data and even repeat rows. In the example, the third row is chosen first, then the first row, and then the third row again, showing how flexible indexing can rearrange and duplicate data as needed. We print the selected rows to show how the array has been reordered and where rows have been duplicated according to the custom row index array. This output makes it easier to see how choosing specific indices changes the arrangement of the original data. By examining the printed result, you can clearly visualize the effect of index-based manipulation on the dataset structure. This script shows how to use row index arrays in NumPy to manipulate data. It starts with an array that pairs identifiers with the heights of 5 people, then prints this original dataset. A separate index array is created to choose specific rows, which is used to reorder and even duplicate rows from the original data. In the example, it selects the fourth row, then the first, and then the fourth again. The printed result demonstrates how row index arrays let you rearrange and repeat rows, providing a flexible way to work with array data in NumPy. Element index arrays. Element index arrays let you select specific elements from an array using precise position coordinates. In a two-dimensional array, one index array specifies row positions and another specifies column positions, and their pairs identify the exact elements to extract. This approach allows you to pull values from many different locations in the array at once. As a result, you can perform flexible data selection without writing loops or repeating indexing steps, making the process more efficient and streamlined. When working with a grid of data, such as locations by pollutants, you can focus on specific location-pollutant pairs by using element index arrays. One array stores the row positions and another stores the column positions of the values you want. Using these two index arrays together lets you pull out all the targeted readings at once, producing a new one-dimensional array in exactly the order you specify. This same idea applies to many tasks, such as selecting particular grades from a gradebook or examining specific pixels in an image. Element index arrays are especially useful for working with higher dimensional data, such as a three-dimensional array with time, latitude, and longitude. By creating separate index arrays for each dimension and aligning them, you can select specific combinations of time and location. This allows you to trace custom paths through the data, like following a storm or sampling chosen waypoints. Using these index arrays, you can encode complex selection patterns, reuse them across similar datasets, and concentrate on the most meaningful data positions, which makes your analysis clearer and easier to maintain. Python code. Element index arrays. Element index arrays let you pick out scattered elements from a larger array rather than taking a continuous block. By using row and column index arrays together, you can precisely select the exact positions you want. This makes it easy to compare the full original grid with a subset of sensor readings chosen through integer indexing. We begin by importing NumPy, a key Python library for efficient numerical computing. It allows us to create and work with arrays and to perform complex mathematical operations quickly. In this script, NumPy is specifically used to build and manipulate arrays so we can select elements by their positions. Having NumPy available is essential for carrying out the tasks planned in this code. We use a numerical grid to store sensor readings in parts per million, where each row represents a different location and each column represents a different pollutant. This structure lets us keep all the measurements in one organized place. Because the data is arranged consistently, we can access and analyze it efficiently for further processing. We use a NumPy array to list the row indices we care about. In this case, 0, 1, and 2, which represent the first 3 rows of our sensor readings grid. Each of these rows corresponds to a different location where pollutants are measured. By defining these row indices, we set up a way to select only those specific rows from the grid. This preparation then allows us to combine these row indices with chosen column indices later, so we can extract particular data points from the sensor readings. We use a numerical computing library to create an array of column indices that lines up with the row indices of our grid. Each row index is paired with a corresponding column index, so together they specify exactly which grid elements to select. In this case, the chosen column indices are set to extract specific pollutant readings, ozone, carbon, and sulfur, from their respective columns in the data grid. We use element index arrays to pick out specific values from the readings grid. NumPy takes the list of row indices and the list of column indices and matches them position by position to form coordinate pairs. Each pair points to one location in the grid, and these locations are then used to extract scattered elements. The result is a new array that contains only the selected readings from the original grid. We begin by printing the full grid of sensor readings so we can see all locations and pollutant measurements before making any selections. Viewing the complete dataset first lets us later compare the original values with the specific entries chosen using index arrays. This comparison helps us verify that the selected values match the intended indices and confirms that our indexing logic is working correctly. We print the array of row indices to make clear which rows are being chosen during advanced indexing. This lets us see exactly how those indices correspond to particular positions in the grid. By viewing the indices directly, it becomes easier to understand and verify how the selection process works. We first display the column indices to see which specific columns of the grid are being selected. This makes it clear how the positions in the grid map to the data we are extracting. Then, we print the selected readings, which are the values taken from the grid using the chosen row and column indices. Each pair of indices picks out a single value. so the result is a one-dimensional array rather than a subgrid or matrix. This script shows how to use element index arrays in NumPy to pull out specific sensor readings from a grid of data. The grid is organized with locations as rows and pollutants as columns. By creating separate arrays for the row positions and the column positions, the code pairs each row with a matching column to select particular readings, such as ozone, carbon, and sulfur. It then prints the original grid, the index arrays, and finally, the chosen readings as a one-dimensional array. This demonstrates how advanced indexing in NumPy allows precise extraction of individual data points. Reordering with fancy indexing. Fancy indexing is a way to reorder data by giving a list of integer positions rather than using simple slices. This lets you rearrange elements in any order you choose, such as moving weekend sales data to the front before the weekdays. It does not sort values automatically, but instead follows the exact index order you specify. As a result, you gain precise control over how data is arranged for analysis or presentation. Fancy indexing is a way to flexibly reorder multidimensional data, such as matrices. For example, in a two-dimensional array where each row represents a patient and each column is a measurement, you can use an array of integer indices to rearrange the rows in any order you need, like grouping patients by treatment type. This reordering keeps all measurements for each patient aligned across columns. As a result, you can separate how the data is physically stored from the logical order that best supports your analysis. Fancy indexing is important in complex workflows such as machine learning, simulations, time series analysis, and image processing, because it lets you rearrange data using arrays of integer indices. For example, when you shuffle a dataset for training and testing, you are creating a random index order to reorder the data without changing its values. Similarly, you can reorder time segments or images to align events or group them by category. In all these cases, the integer index array acts as a flexible, precise, and reproducible guide for structuring the data. Python code. Reordering with fancy indexing. You can use NumPy's fancy integer indexing to reorder elements in an array without changing their values. For example, you might take daily sales data and apply a custom array of integer positions to rearrange the days into a new order. This technique simply changes where each value appears in the array, while the underlying sales numbers themselves remain exactly the same. It is a powerful way to quickly reorganize data based on any index order you choose. The script starts by importing the NumPy library, a key tool in Python for efficient numerical computing. NumPy is used here to handle arrays that store sales data and to perform mathematical operations on them. In this context, it enables operations like reordering elements through advanced indexing. This setup allows the sales data to be rearranged as needed without changing the original values. We use a NumPy array to store weekly sales in dollars, with one value for each day from Monday through Sunday. This gives us a clear, ordered structure where each position in the array corresponds to a specific day's sales. With the data in this form, we can easily apply NumPy's array operations to manipulate and analyze sales for individual days or for the entire week. We create a list of day labels that names the days of the week from Monday through Sunday. This list lines up each day with its position in the sales data. By matching these positions, we can easily look up sales for a specific day. It also lets us reorder or organize the sales information based on the day of the week. We begin by displaying the days of the week alongside their sales values. To do this, we pair each day label with its corresponding sales figure using a function that combines the two arrays into matching pairs. We then convert these pairs into a list, so the data is easy to read. This gives us the sales information in chronological order, clearly showing each day and its sales amount. We build an index array to reorder the sales data, so that weekend days come first, followed by weekdays. In this array, the positions for Saturday and Sunday are listed first, and the positions for Monday through Friday follow. Using this custom order, we rearrange the sales data to clearly separate and highlight weekend sales from weekday sales. We use fancy indexing to reorder the sales data by rearranging the original sales array according to a set of reorder indices. This produces a new array where the sales values appear in the desired order, such as placing weekend sales first. We then apply the same reorder indices to the day labels, so that the days of the week are rearranged in exactly the same way. This keeps each day correctly matched with its corresponding sales figure after reordering. We begin by printing a short message to explain that the data will now be shown with weekend days first. Then we use a pairing step that matches each day label with its corresponding sales value, forming a list of day and sales pairs. When we print this list, it clearly shows the reordered data, with weekend days appearing before the weekdays, so we can see the effect of the new ordering. We first print a short message to indicate that we are about to display the original sales data. Then we print the sales array itself to show the original values. This confirms that the data has not changed after using fancy indexing earlier in the script. Verifying that the original array remains unchanged is important, because reordering operations can sometimes accidentally modify the underlying data. This script shows how to reorder elements in a NumPy array using fancy indexing. It uses a weekly sales array with dollar amounts for each day from Monday through Sunday, then prints the original order of days and sales. A custom index array is created to rearrange the data so that weekend sales appear first, followed by weekday sales. The script prints the reordered sales with their day labels to illustrate the new sequence. It also confirms that the original sales array does not change, demonstrating that fancy indexing creates a reordered view without modifying the underlying data. Boolean masks and where. Element-wise comparisons. Element-wise comparisons let you create Boolean masks by checking each element of an array independently. When you compare an array to a single value or to another array of the same shape, you get a new array of true or false values that matches the original structure. This gives a detailed pattern showing where a condition is met rather than a single overall result. For example, comparing daily temperatures to the freezing point produces a Boolean array indicating which days are above or below freezing. The main idea is that these comparisons preserve the data layout while encoding whether each element satisfies the condition. Element-wise comparisons let you apply checks like less than, greater than or equal to, and equality to every entry in an array, producing a matching array of true or false values. This is useful for tasks such as comparing air quality readings to regulatory limits to find safe areas, or comparing data from different days to track changes. In finance, you can compare stock prices to a target to find days when the stock closed higher. Overall, these comparisons turn raw numerical data into clear, logical patterns that highlight the values that meet your criteria. Element-wise comparisons rely on array shapes and broadcasting rules so that values line up correctly. When an array is compared to a single number, that number is treated as if it were copied to each position in the array. When two arrays are compared, they must either share the same shape or be compatible through broadcasting so each element has a matching partner. This allows position-specific checks, such as comparing scores across semesters or pixel brightness against a reference, and produces boolean masks that are useful for precise data filtering and analysis. Python code, element-wise comparisons. Use simple temperature values in Fahrenheit to demonstrate element-wise comparisons, where each temperature is checked against a condition such as being above a certain threshold. These comparisons produce Boolean arrays that have the same shape as the original temperature data. Each position in the Boolean array shows whether the corresponding temperature meets the condition. This helps beginners see how masks represent the result of a condition applied to every individual element in the data. We begin by importing the numerical computing library NumPy in Python. This library is essential for working efficiently with arrays of data. It allows us to perform fast, vectorized operations on these arrays, which is especially important for the element-wise comparisons we will use later in the code. We begin by using a NumPy array to store the daily high temperatures for a week in Fahrenheit. Each element in the array represents the high temperature for one day. Using a NumPy array lets us perform fast numerical operations on all the temperatures at once. It also makes it easy to compare values and manipulate the data later in the script. We compare each temperature in the array to the freezing point of 32 degrees Fahrenheit to see which days were above freezing. This comparison is done one element at a time and produces a new array of true or false values. Each value is true if that day's temperature is above 32 degrees, and false if it is at or below freezing. This Boolean array, called the above freezing mask, makes it easy to identify all days with temperatures above freezing. We create a Boolean mask called very warm mask that checks each value in the temperatures array to see if it is at least 55 degrees Fahrenheit. For every temperature, the mask records true if it meets or exceeds this threshold, and false if it does not. The result is a new array of true and false values with the same shape as the original temperature data, indicating which days are considered warm. We begin by printing the array of temperatures in Fahrenheit to see the original data we are working with. Viewing these values prepares us to compare them with the Boolean masks we create next. This visual comparison helps us connect each temperature to the conditions we are analyzing, such as whether it is above freezing or very warm. This line prints which days have temperatures strictly above the freezing point. It relies on a previously created true or false mask that checks whether each temperature in the array is greater than 32 degrees Fahrenheit. The output shows a series of true or false values, one for each day. This makes it easy to see which days are warmer than freezing. This line prints which days are considered very warm by using the Boolean mask created earlier. The mask checks whether each day's temperature is at least 55 degrees Fahrenheit. The output shows true or false for each day, making it easy to see which days meet the warm day threshold. This step checks whether each day's temperature is higher than the previous day by shifting the temperature data by one position and comparing each value to the one before it. The result is a series of true or false values showing which days were warmer than the day before. This makes it easy to see overall trends in how temperatures change over the week. This script uses NumPy to compare daily high temperatures over a week. It creates one set of true or false values showing which days were above freezing, and another showing which days were very warm, defined as 55 degrees or higher. It also checks whether each day was warmer than the previous day. When run, it prints the original temperatures and these Boolean results, making it clear which days meet each condition. Combining Boolean masks. Once you understand simple Boolean masks, the next step is to combine them using logical operators. Each mask answers a yes or no question about every element in an array, and by using logical and, or, and not, you can express more complex conditions. This lets you check whether values fall within a range, or satisfy several requirements at once. The resulting combined mask can then be used to filter or index the array in a single, efficient step, instead of applying multiple filters or control structures. When working with a large dataset of patient records, you can use logical masks to focus on specific groups. For example, you might create one mask for patients above a certain age, and another for those with high blood pressure. Combining these masks with a logical and selects only patients who meet both conditions, while using a logical or with masks for smokers and high blood pressure selects patients who meet either condition. You can also apply a logical not to invert a mask, such as turning a smoker mask into a non-smoker selection. These operations let you target exactly the subsets of patients you want to analyze. When building complex data analyses, you often combine several logical conditions in sequence, so the order of these operations matters. For instance, in a financial dataset, you might select transactions that are large and occur on weekdays, or any that involve a high-risk merchant, using logical and, or, and not to combine masks for amount, day, and merchant category. The result is a single composite mask that lets you extract all rows matching your criteria in one step. By practicing with different scenarios, such as filtering sensor data by location and time, or selecting students based on multiple requirements, you learn to translate real-world conditions into effective combinations of Boolean masks. Python code, combining Boolean masks. This section shows how to combine Boolean masks with simple NumPy arrays to filter values. it demonstrates how logical and, logical or, and logical not work when applied to these masks. By printing the results of each operation, beginners can clearly see which elements of the array are selected or excluded. The goal is to help learners understand how combined conditions control which array values are kept. In this script, we use the NumPy library, a key tool in Python for efficient numerical computing. NumPy lets us work with arrays and many mathematical functions, which is especially useful for large datasets. Here, it is used to create and manage arrays that store temperature data. With these arrays, we can apply logical operations and masks to filter and analyze the temperature values effectively. We begin by creating a NumPy array that stores several temperature values in Fahrenheit. Using a NumPy array lets us handle all these temperatures as a single dataset. This makes it easy and efficient to perform operations and comparisons on every value at once. We will use this array to show how boolean masks can filter temperatures based on specific conditions. We create two boolean masks to categorize the temperature data. The first mask marks warm days, where the temperature is at least 70 degrees Fahrenheit. The second mask marks very hot days, where the temperature is 90 degrees or higher. Each mask is a true or false array that helps separate the data into useful temperature ranges for further analysis. We are combining two Boolean masks with a logical AND operation. The first mask marks warm days with temperatures of at least 70 degrees Fahrenheit, and the second marks very hot days with temperatures of at least 90 degrees. When we apply the logical AND, we get a new mask that keeps only the days that satisfy both conditions, which in practice means days with temperatures of 90 degrees or higher. This combined mask is then used to filter the array so we can focus on days that meet both criteria at the same time. We combine two Boolean masks using a logical OR to capture a wider range of high-temperature days. One mask marks warm days and the other marks very hot days. When we apply the logical OR, we get a new mask that includes any day that is either warm or very hot. We then use this combined mask to filter the temperature data, so it includes all days that meet at least one of these higher temperature conditions. We use the logical NOT operator to reverse the warm days mask by flipping each true value to false and each false value to true. This creates a new mask that highlights all days that are not warm. In other words, it selects the cooler or colder days in the temperature data. We begin by printing the original Fahrenheit temperatures to see the data we are analyzing. Then we display a warm days mask, a set of true or false values that marks where temperatures are 70 degrees or higher, so we can quickly spot warm days. Next, we show a very hot days mask, which similarly marks where temperatures reach 90 degrees or higher, identifying very hot days. Viewing these masks alongside the original data makes it easy to see how each condition classifies the temperatures. The code first prints the original Fahrenheit temperatures, then shows Boolean masks that mark warm days at 70 degrees or higher and very hot days at 90 degrees or higher. It combines these masks with a logical AND to select temperatures that are both warm and very hot, and with a logical OR to select temperatures that are either warm or very hot. It also uses a not warm mask to pick out cooler days that do not meet the warm threshold. Together, these steps demonstrate how different Boolean masks can be combined to filter temperature data in multiple ways. This material explains how Boolean masks in NumPy can be used to filter temperature data. It creates an array of Fahrenheit temperatures and defines one mask for warm days at 70 degrees or higher, and another for very hot days at 90 degrees or higher. These masks are then combined with logical AND to find days that are both warm and very hot, and with logical OR to find days that are either warm or very hot. A logical NOT operation is also used to identify days that are not warm. Printing the original temperatures alongside these results shows clearly which days meet each condition and illustrates how Boolean logic helps filter data in NumPy arrays. Conditional selection with where. Boolean masks let you select array elements based on true or false conditions, acting like a vectorized if-else across the entire array. You first define a condition that creates the mask, then provide one array of values to use where the condition is true, and another for where it is false. The result is a new array that efficiently combines these choices without needing explicit loops. This approach uses Boolean masks to transform data based on simple criteria like thresholds or categories. For example, with daily temperature data, you can mark days as heatwave or normal by masking temperatures above a chosen level and assigning labels in one step. In finance, you can similarly detect negative returns with a mask and replace them with a penalty value, while leaving positive returns unchanged. Overall, this method condenses complex conditional logic into a single array operation, making code both more efficient and easier to read. Boolean masks are a powerful tool for conditional selection in data cleaning and feature engineering. They let you flag values that meet certain conditions, such as invalid negative distances in sensor data, and then standardize or replace those values while keeping valid data intact. You can also combine conditions like age and income to identify high-risk cases and assign appropriate scores. This approach makes it possible to apply complex decision rules across entire arrays efficiently, without writing explicit loops, which keeps transformations clear and easy to manage. Python code, conditional selection with where. This section explains how to use the NumPy where function to make simple conditional selections, such as assigning temperature labels. You create a Boolean mask that marks which values meet a condition, like temperatures above a certain threshold. Then, you provide two small arrays of labels, for example, one for higher temperatures and one for lower temperatures. The Boolean mask tells NumPy where to pick from each label array, so every temperature gets the correct label. The goal is to keep the example small, clear, and beginner-friendly, so learners can quickly see how conditional selection works. In this lesson, we use the NumPy library in Python, which is designed for fast numerical computations with arrays. Here, NumPy helps us store and work with a set of temperature values efficiently. By using NumPy, we can easily apply conditions to this temperature data and create labels based on specific rules. This makes it straightforward to analyze and categorize the temperatures in a flexible and efficient way. We begin by using NumPy to create an array that stores daily high temperatures in Fahrenheit. Each value in the array represents the high temperature for a different day. Because the array is small and simple, it is easy to use for demonstration. This structure lets us apply operations to the entire set of temperatures efficiently, taking advantage of NumPy's strengths with numerical data. We set a heatwave threshold at 90 degrees Fahrenheit to serve as a benchmark for identifying heat wave days. Any temperature at or above this value is considered part of a heat wave. Using this threshold, we can later create a true or false mask that marks which days meet or exceed the threshold. This allows us to categorize days based on whether they qualify as heatwave days. We create a boolean mask by comparing each temperature in the array to the heatwave threshold. For every temperature, we check whether it is greater than or equal to that threshold. This comparison produces a new array of true or false values. Each true value marks a temperature that meets or exceeds the threshold, and each false value marks one that does not. We then use this mask to identify which days are considered heatwave days. We use the where function from NumPy to choose between two labels for each temperature in the array. It checks each value against the Boolean mask created earlier. When the mask is true, meaning the temperature meets or exceeds the heatwave threshold, it assigns the label heatwave day. When the mask is false, it assigns the label normal day. This applies the condition efficiently to the whole array and produces a new array of labels that match each temperature value. We begin by displaying the array of temperatures in Fahrenheit so we can clearly see the original data. This initial view helps us understand what values we are working with. It also provides a reference point for comparing how the data changes after we apply our conditional operations. We print a Boolean mask that shows which days meet the heatwave condition. This mask is an array of true or false values, where each value tells us if the corresponding temperature is at or above the heatwave threshold. By looking at this mask, we can quickly identify which days are classified as heatwave days based on the temperature data. Finally, we display the labels assigned to each temperature value. This output indicates whether each day is classified as a heatwave day or a normal day, based on the conditions defined earlier. It clearly shows how the NumPy where function used the Boolean mask to categorize each temperature into one of these two groups. This example shows how NumPy can label daily temperatures as either heatwave days or normal days, using a simple threshold. It starts with an array of temperatures in Fahrenheit and sets 90 degrees as the cutoff. A Boolean mask marks which temperatures are at or above this threshold, and a conditional selection then assigns the label heatwave day to those values and normal day to the rest. When run, the script outputs the original temperatures, the true or false mask, and the final labels, illustrating how NumPy efficiently applies conditional logic across an entire array. In-place array updates. Masked value assignment. Masked value assignment is a way to update only selected elements of an array while leaving the rest unchanged. You first create a mask, which is an array of true or false values that marks which elements meet a given condition. You then use this mask to assign new values to just those marked elements in a single, efficient step. This approach is especially useful for large datasets because it clearly specifies which entries to modify and avoids checking each element one by one. In data cleaning, masked assignment is a way to change values only where certain conditions are met. You first create a mask that flags data points you want to fix, such as unrealistic temperature readings or negative values in financial data, where only non-negative values make sense. You then use this mask to replace those flagged values with a placeholder or default value. This approach lets you apply consistent corrections across the dataset efficiently in a single step. Masked value assignment becomes especially useful when you combine several conditions to focus on specific parts of a dataset. For example, in health data, you might only adjust values for patients above a certain age whose measurements fall outside safe ranges. By building a mask from these conditions, you can update just those entries, such as capping extreme values or filling in missing data. This lets you apply complex logic in a clear, efficient way and produce cleaner, more reliable data for analysis across many fields. Python code, masked value assignment. This section shows how to use masked value assignment with simple temperature data. You learn how Boolean masks can be used to pick out unrealistic temperature readings. Then, using vectorized masked assignment, you replace those unrealistic values directly in the data. This demonstrates an efficient way to clean temperature measurements by updating only the values that fail a chosen realism test. The script starts by importing the NumPy library, a key tool in Python for fast numerical computing with arrays. NumPy is used here to create and work with arrays of temperature data. It allows efficient vectorized operations and makes tasks like applying masked assignments to parts of the data straightforward and efficient. We begin by using a numerical computing library to create an array of daily temperatures in Fahrenheit for several cities. This sample data includes realistic values like 55, 68, 72, and 49 degrees, as well as unrealistic values such as -40 and 130 degrees. The purpose of this array is to provide a simple dataset we can use to demonstrate how to detect and clean temperature readings that fall outside a reasonable range. We set a realistic temperature range for our dataset by defining the minimum as 0 degrees Fahrenheit and the maximum as 120 degrees Fahrenheit. This range represents the acceptable values for temperature readings. Any data point below 0 or above 120 is treated as unrealistic and flagged as potentially incorrect. We create a Boolean mask to flag temperature values that fall outside a realistic range. For each temperature, we check whether it is less than the chosen minimum or greater than the chosen maximum. This produces an array of true or false values, where true marks an unrealistic temperature. We will later use this mask to selectively replace those unrealistic values while leaving the others unchanged. We start by printing the original array of Fahrenheit temperatures so we can see the data before any changes. Then we print a Boolean mask that marks which temperature values are unrealistic. In this mask, each position is true if the corresponding temperature falls outside the realistic range and false otherwise. Viewing both the original temperatures and this mask together makes it clear which values will be replaced in the next steps. We handle unrealistic temperature readings by assigning them a special placeholder value that represents missing or invalid data, using the not a number value from the numerical library. A Boolean mask identifies which temperature entries are unrealistic. We then apply this mask to the temperature array so that every value flagged by the mask is replaced with the not a number placeholder. This process cleans the dataset by clearly marking out-of-range temperatures while leaving all valid readings unchanged. Finally, the program prints the cleaned temperature array, where any unrealistic values have been replaced with a placeholder value, in this case, not a number. This output lets you see which entries were flagged and changed by the masked assignment. As a result, the data is now sanitized, with outliers effectively removed from further analysis. This script shows how to clean a dataset of temperature readings using a numerical computing library. It begins with an array of Fahrenheit temperatures that includes some unrealistic values. The code creates a boolean mask to flag any temperatures below 0 or above 120 as outliers. It then uses this mask to replace those unrealistic values with a placeholder value, specifically not a number. The result is a cleaned temperature array where invalid readings have been sanitized and clearly marked as missing data. Indexed assignment basics. Indexed assignment lets you directly change selected parts of an array, as if you were editing specific cells in a grid. By choosing indices on the left side of an assignment, you control exactly where new values are placed, whether you update a single entry or a larger region. This method is especially useful in data work because it lets you fix errors or insert new values without changing the array's overall shape or making extra copies of the data. Indexed assignment means you can use the same indices you use to read data to also write or update it. By selecting a subset of entries with positions or slices, you can assign new values exactly to those locations, such as updating a column in the first 10 rows or changing every third time step. The important idea is that indexing is not only for accessing data, but also for precisely modifying it. This symmetry lets you first test your selection when reading, then confidently apply it to update the data in place. Indexed assignment is a way to update only selected parts of multidimensional data, such as specific regions in an image or particular accounts and time periods in a financial dataset. By modifying values in place instead of creating new arrays, it improves efficiency and keeps the data structure easier to understand. Practicing this technique on complex subsets strengthens your ability to perform advanced data cleaning and transformation while keeping code concise and memory usage low. Python code. Indexed assignment basics. This section focuses on basic NumPy indexed assignment using simple table-style data. It shows how to update entire rows, entire columns, and individual cells directly in place. The goal is to help you see how the same indexes you use for reading values can also be used to write and update values. By practicing these operations, you learn to modify array data efficiently without creating new copies. We begin by using the NumPy library, which is a core tool in Python for working with arrays and doing fast numerical calculations. NumPy gives us the functions and data structures we need to efficiently store, access, and modify our data. This will allow us to perform indexed assignments and other array manipulations in a clear and efficient way. We create a two-dimensional array using NumPy to store daily temperatures in Fahrenheit. This array has 3 rows and 3 columns. Each row represents a different day. and each column represents a different time of day. The numbers in the array are the temperature readings for those specific days and times. We begin by displaying the original temperature data so we have a clear reference before making any changes. Seeing this initial state helps us understand what the data looked like at the start. It also makes it easier to compare later and see exactly how the updates affect the array. In short, printing the original data sets a baseline for interpreting all subsequent modifications. In this example, we update a single cell in a two-dimensional NumPy array by accessing the element in the first row and second column and changing its value to 71. This action directly modifies the existing array rather than creating a new one. It allows us to quickly correct or adjust individual data points within the array as needed. In this example, we update an entire row in a two-dimensional array to fix a day's temperature readings. We select the second row using its index, which is 1, and replace it with a new set of corrected values, 76, 78, and 74. This change is done in place, meaning we directly modify the existing array rather than creating a new one. We adjust the first column of our data array, which holds the morning temperature readings, by selecting all rows in that column and subtracting 2 from each value. This change is done directly on the original array, so the data is modified in place rather than copied. As a result, the entire column is efficiently updated without creating a new array or using extra memory. In this example, we use slicing in a NumPy array to update several values at once. We select the last 2 rows and the third column, then add 1 to each of those elements. Conceptually, this represents increasing the temperature readings for the last 2 days by 1 degree Fahrenheit. This shows how slicing lets you efficiently modify multiple array elements in place without changing the rest of the data. We now display the updated temperature data to confirm that our indexed assignments worked as intended. By printing the modified array, we can see how specific cells, as well as entire rows and columns, have changed. This output lets us verify that the in-place modifications were applied correctly. In other words, the printed result shows the new temperature readings after all updates have been made. This script shows how to use indexed assignments to modify parts of a two-dimensional NumPy array that stores daily temperatures in Fahrenheit. It first prints the original data, then changes a single temperature value at a specific row and column. It goes on to replace an entire row to correct 1 day's measurements, and adjusts the first column by subtracting 2 degrees from each morning reading. Finally, it increases the last column's values for the last 2 days by 1 degree and prints the updated array, illustrating how to efficiently change selected entries in place. Value clipping techniques. Value clipping is a method for keeping array values within a chosen range, so that extreme outliers do not distort data analysis. It works by raising any values below a lower limit up to that limit, and lowering any values above an upper limit down to that upper limit, while leaving all other values unchanged. Using advanced indexing, you can apply this adjustment only to selected parts of an array or to values that meet certain conditions, without creating extra copies of the data. For example, in a temperature dataset, readings outside a realistic range can be clipped, so the data stays consistent while overall patterns are preserved. When using value clipping with advanced indexing, you create Boolean masks to find elements that fall outside a desired range, and then replace those values with the appropriate boundary limits. This approach lets you selectively clip only certain parts of an array, such as particular assets in financial data or specific color channels in images. Because the updates are applied directly to the original array, it is memory efficient and avoids creating temporary arrays, which is especially important for large datasets. Beyond using a single global limit, you can apply value clipping in a more targeted way by using indexing to set different ranges for different parts of your data. For example, each column in a feature matrix can have its own clipping range, such as one for age, another for income, and another for sensor readings. In a three-dimensional array, you can first index specific times or locations and then apply masks only there. This lets you embed domain knowledge, like regulatory limits or survey caps, directly into your clipping operations while keeping them efficient and localized. Python code. Value clipping techniques. This section explains how to limit extreme temperature values in NumPy arrays. You learn to use Boolean masks to identify and clip out-of-range temperatures, and to perform in-place updates so that only the selected positions in the array are modified. It also shows how to use advanced indexing so that different rows can be clipped using different allowed ranges, giving you fine-grained control over the adjustments. We begin by using the NumPy library, which is a key tool in Python for fast numerical calculations and working with arrays. In this script, NumPy helps us store and process temperature data efficiently. We also use it to clip or limit the temperature values, so they stay within specific minimum and maximum bounds. This ensures the data remains valid and within the desired range during our analysis. We begin by creating a two-dimensional NumPy array that stores Fahrenheit temperatures for 3 cities over 5 days. Each row represents one city and each column represents one day. The array includes some extreme temperature values, such as 120 and -40, so we can later see how to handle outliers. We explicitly set the data type to float so that later operations, like clipping values, are accurate and preserve numerical precision. We begin by displaying the original array of temperatures in Fahrenheit to establish a clear baseline. Seeing this initial state lets us understand the data before any changes are made. This baseline is important because it allows us to compare the unmodified temperatures with the final values after we apply the clipping techniques. We define a global minimum temperature of 0 degrees Fahrenheit for all cities in our dataset. This value represents the lowest plausible temperature we expect to see. Any recorded temperature below this threshold is treated as an outlier. Such values are then adjusted to meet this minimum, helping keep the data consistent and realistic. We set a global maximum temperature of 120 degrees Fahrenheit as the upper limit for physically plausible values in our dataset. This threshold defines what we consider realistic temperatures across all cities. Any recorded temperatures above this value can then be identified and clipped, helping keep the data within reasonable bounds. We create a Boolean mask to find temperature values that fall below a predefined global minimum. This is done by comparing each temperature in the array to that minimum value. The comparison produces a new array of true or false values, where true marks temperatures that are too low. We then use this mask to selectively update only those low temperatures so that all values meet the required minimum. We create a boolean mask to find temperature values that exceed a global maximum threshold. This is done by comparing each temperature in the array to the maximum value. The comparison produces a new array of true or false values, where true marks temperatures that are too high. We then use this mask to selectively modify only those high temperatures so they can be clipped down to the maximum allowed value. This step updates the temperature array by forcing any values below the global minimum threshold up to that minimum value. It uses a Boolean mask to locate only the entries that need changing, so unaffected values remain the same. The update is done directly on the original array rather than creating a new one, which saves memory and improves efficiency. The code adjusts the temperature array by capping any values that are higher than a defined global maximum. It first creates a mask that marks all positions where the temperature exceeds this limit. Then it replaces those values with the maximum allowed temperature. This process clips overly high temperatures so that no value in the array goes beyond the specified maximum. To apply a more specific clipping range to only the second row of temperatures, we first select that row by setting the city index to 1. This step isolates the data for the second city so that any clipping or further processing affects only that row and not the entire dataset. By targeting this specific index, we can control and refine the temperature values for just that city. We set a minimum temperature threshold of 20 degrees Fahrenheit specifically for the second city. This value defines the lowest acceptable temperature for that row of data. By doing this, we can later clip the temperature values more precisely. As a result, the recorded temperatures for the second city stay within a realistic and meaningful range. The code sets a maximum temperature of 100 degrees Fahrenheit for the second city, creating a tighter limit for that specific row of data. Any temperature values above this limit are clipped down to the maximum. This is part of a broader approach where different clipping thresholds are applied to different cities, allowing more precise control over the temperature values in each part of the dataset. Here we focus on the second row of the temperature array, which represents the second city. By selecting only this row, we isolate that city's data from the rest. This allows us to apply a specific range of temperature limits tailored to that city alone. With the row isolated, we can then perform targeted clipping operations on its values. We create a mask for the second city's temperature row to find values that fall outside a chosen range. For each temperature, we check whether it is below the city's minimum or above the city's maximum. This produces a Boolean array that marks which positions are out of bounds. We then use this mask to selectively clip those out-of-range temperatures so they stay within the desired limits. We update the temperatures in the second city row by using advanced indexing with a mask that selects only the values outside the allowed range of 20 to 100 degrees Fahrenheit. We then pass these out-of-range values to the NumPy clip function, which forces them into the specified limits. This adjustment is applied directly to the original array, so the data is modified in place without creating a separate copy. Now we display the final temperatures after all clipping operations have been applied. This output shows the adjusted array where extreme values have been brought within the chosen lower and upper bounds. Because the changes were made directly to the original data, the printed results reflect those in-place modifications. Overall, This demonstrates how clipping ensures that every temperature value stays within the specified limits. This script shows how to use NumPy to clip extreme temperature values in a dataset. It starts with a 3x5 array of Fahrenheit temperatures for 3 cities over 5 days, then prints the original values. The script first applies global clipping so that any value below 0 is set to 0, and any value above 120 is set to 120, using boolean masks to modify the array in place. It then narrows the range for the second city only, forcing its temperatures to stay between 20 and 100 through advanced indexing. Finally, it prints the updated array to illustrate how indexing and masking can clean and correct out-of-range data directly within a NumPy array. In this lecture, you learned to apply integer array indexing to select arbitrary rows, columns, and elements from ndarrays. Construct Boolean masks to filter arrays based on element-wise conditions, and combine conditions with logical operators. And use advanced indexing patterns to modify subsets of arrays in place for data cleaning and transformation tasks. In the next module, Module 3, we will go over broadcasting and I/O.
Thank you for your attention. See you all in the next lecture.